So we'll begin with a quick recap of precision, accuracy, and significant figures. And then we'll review the rules for significant figures and then take a quiz on the activity. So in our discussion last week, so we discussed the difference between accuracy and precision. One has to do with how close the measurement is to the target or to the expected value. And the other one has to do with how reproducible the result is. One is tied to the person carrying out the experiment, that's accuracy, and the other one is tied to the instrument used to measure or to carry out the experiment. So just a quick vote in the chat. So use the chat and type in your answers. So which option correctly describes the measurement below? You have 4 options: accurate and precise, accurate but not precise, not accurate but precise, neither accurate nor precise. Okay, so, and A is the correct response. So the 4 dots represents the measurements, and the red dot at the center represents the target. So all the 4 measurements are clustered together and also close to the target. So that represents an accurate and precise measurement. Here, which option correctly describes the measurement? Again, 4 choices. So go ahead and enter your responses in the chat. Okay, so everyone says B, and B is the correct answer. So the 4 dots are indeed close to the target. That means the 4 measurements are accurate. However, the 4 measurements are not reproducible. So each time the measurement was repeated, it fell at a different spot. So that means the measurement is accurate but not precise. And here we have another option. So which of the 4 options describes the measurement in this slide? Okay, so everyone says C, and let's see. C is indeed correct. So if you can see the 4 measurements are almost on the same spot. However, the distance from the target to where the measurements land is quite significant. So you would say this measurement is not accurate, but it's precise because the dots are almost on top of each other. And finally, we have this situation with the dots scattered all over the place. How would you characterize this? Okay, so the class says D, and D is indeed correct. So the measurements described by this figure are neither accurate nor precise. They're not accurate because they're far away from the target, which is the center dot. And then they're not precise because the measurements are not reproducible. The measurements are far from each other. So let me switch us to the next presentation. And let me know if you can see this presentation on the rules of significant figures. Can you see the slides for the rule?
We can see it.
All right, great. Again, this is just a refresher because most of you are familiar with the rules, but I did notice that there was some confusion on how to count significant figures. And I cannot overemphasize how important this topic of significant figures is when it comes to measurements in chemistry, in biology, in physics, in any science lab. So when you're doing calculations, your professors will expect you to be able to round your answers correctly without asking the instructor each time, how many decimal places do you want me to keep? How should I round my answer? Again, rounding your answers is not determined by what your professor likes or does not like. It depends on the rules, which we're going to review now. So let's first understand what are significant figures. So a significant figure is a digit in a numerical value that contributes to the overall precision or accuracy of the measurement or calculation. It represents a meaningful and reliable digit obtained from a measurement or calculation result. So it's, in short, it's a reliably known digit. It's a digit that contributes to the accuracy or the precision of the measurement. Significant here doesn't just mean important. It means it's reliably known. So rule number one governs non-zero digits. So all non-zero digits in any measurement are significant. So this number has three significant figures because all of the digits are non-zero. So if a number had 10 non-zero digits in it, then all those 10 non-zero digits will be significant. Rule number two, zeros between non-zero digits. Again, this is simple. All zeros between two non-zero digits are significant. All non-zero digits are significant, and any zero sandwiched between two non-zero digits are also significant by default. So in this example, 2051, the zero is significant because it's sandwiched between 2 and 5. So we have 4 significant digits in this number. Rule number 3, leading zeros. What are leading zeros? These are any zero that comes before the first non-zero digit in a number is classified as a leading zero. It doesn't matter whether the number has a decimal point or not. Any zero that comes before the first non-zero digit is classified as a leading zero, and it's nothing but a placeholder. So it's important because it helps the number retain the correct magnitude. If you just discarded the leading zeros, it will change the magnitude of the number. So you could not say leading zeros are not important. That's why I said from the beginning that the word significant doesn't just mean important or not important. It means reliably known. So in this example, 0.54 has two significant digits because the zero in 0.54 is a leading zero. It's just a placeholder. It doesn't change, communicate the precision or the accuracy of the number. The number 0.0032 also has two significant figures because all the three zeros are leading zeros. Remember, a leading zero is a zero that comes before the first non-zero digit. Rule number 4, trailing zeros. And this is where you need to be very attentive because this is a little bit tricky. Now, as we proceed, in the meeting, if you look at the Zoom meeting, the toolbar, there is a Q&A tab. If you have a question while the class is in progress, just type your question under the Q&A. So that's meant for questions. Rule number 4, trailing zeros to the right of the decimal are significant. So we will define trailing zeros as zeros that come, at the end of the number and also after like a non-zero digit. Because if the zeros come before non-zero digit, those are leading zeros. If the zeros are sandwiched between two non-zero digits, by default, they're significant. So you don't count them as trailing zeros. So trailing zeros are strictly like the zeros at the end of a number. So if the zeros are located at the end of the number and to the right of a decimal point, then all the trailing zeros will be counted as significant. In this example, we have 4 significant figures in 92.00 and 5 significant figures in 92.000 because all the trailing zeros in these two numbers are significant. Number one, they're at the end of the number and then after a decimal place or to the right of a decimal place. Rule number 5, trailing zeros in a whole number. So trailing zeros in a whole number with the decimal shown as significant. Now remember, placing a decimal at the end of a whole number is usually not done, but by convention, if this is done, it indicates that all the zeros in that whole number are significant. What do I mean? In this example, 540 with a decimal point at the end indicates that the 0 after 4 is significant. Hence, this number will have 3 significant figures. Now, what if there is no decimal place in the whole number? So this is where we have a complicated situation. So this is ambiguous. That means when you have zeros at the end of a whole number, let's say 1,000 or 2,500 with no decimal point, then we have a confusing situation where the zeros may be significant or not. So in 540, the 0 may or may not be significant. And there could be 2 or 3 significant figures in this number. So when you see a whole number with zeros at the end and no decimal point, it's difficult to say. Some, scientists will say any zero at the end of a whole number is not significant, but I will show you situations where the zero may be significant. Because if you had a number like, let's say 544, and they say, round this number to, that's probably not the best example. I'll give you an example later on, but the situations where the zero, may be significant and you just cannot, discard it. But the important point to note here is to remove this ambiguity, we have what is called scientific notation, which is explained in rule number 8. So when you have a situation where the zero could be misinterpreted as significant or not, to remove the confusion, you can write the number in scientific notation. So if we write 540 as 5.40 times 10 to the 2, we are communicating the fact that this number has 3 significant figures. If we wrote the same number as 5.4 times 10 to the 2, then we're saying that it has just 2 significant figures. But note that 5.40 times 10 to the 2, 5.4 times 10 to the 2 have exactly the same size, 540. So whenever you find yourself in a situation where there could be confusion on the number of significant figures, the best approach is to write the number in scientific notation. Rule number 7, exact numbers or constants. So an exact number or constant is assumed to have an infinite number of significant figures. So these are numbers that are used to define certain quantities or constants. For instance, the conversion factor between, let's say, meters and kilometers and so on. The unit of length, the SI unit of length is the meter. So when you're dealing with conversion factors, you work with the assumption that you have an infinite number of decimal places after the decimal point. Constants, like the acceleration due to gravity, even though the textbook may just give it to you as a 9.8 meters per second squared, you would assume that it has an infinite number of decimal places in the end. So you wouldn't use the two significant figures in a 9.8 to determine the result of your calculation. So basically, when you're doing calculations, the number of significant when you're doing calculations, you don't consider constants or conversion factors when applying the rules for significant figures. You only consider, the number of significant figures in the measurements. And then rule number 8, scientific notation. So scientific notation is often written in the form n times 10 to the power y. So all digits comprising the number n are significant by the first 6 rules. The 10 and the y are not significant. So for instance, 5.02 times 10 to the 4 has 3 significant figures because 5.02 has 3 significant figures. 10 is the base and 4 is the power. Those are not significant. They're just used to represent the size of the number. So here are the rules summarize all non-zero digits are significant. Zeros that are sandwiched between two non-zero digits are significant. Leading zeros are not significant, they're just placeholders. Trailing zeros to the right of a decimal are significant. Trailing zeros in a whole number with a decimal shown are significant. But when there is no decimal in a whole number, trailing zeros are ambiguous because they may be significant and they may not be in certain situations. So to remove the ambiguity, it's recommended that you write the number in scientific notation. And then exact numbers and constants, for instance, the constant pi 3.14 is also assumed to have infinite number of decimal places. So an infinite precision, infinite accuracy. For number in scientific notation, in the format n times 10 to the power y, all the digits comprising the radical of the n are significant. 10 and y are not. So that summarizes the rules for significant figures. Are there any questions or comments?
No, sir.
No, okay. So we will proceed with,
Actually, wait. Are we able to see this summary somewhere?
yeah, so you should have access to this summary in the course. Let me see. So if you go to the announcement section, I actually posted a quiz, an interactive like flashcard lesson for the rules on significant figures. How many of you were able to access this? Can you see the announcement page? So right here. Yep, this is probably expired because it's no longer live, but I'm going to post this slide in the course, nonetheless, under the announcement section. Let me go to we have an interactive quiz for today, so just give me a moment. Let me pull that up. Okay, can you see the quizzes screen?
Yes, we can see it.
Okay, so you can join by going to joinmyquiz.com. Let me post that link into the chat. And enter the codes 378146. And I'm going to start. So once you join, you can begin the quiz. All right, let's go faster. We have around 5 more minutes for this activity. At the end of the quiz, you should be able to, know which aspects of the significant figures rules need to review. But the quiz will give you enough practice to see which of the rules you've mastered or not. Okay, I'm about to end the activity in 2 minutes. I say 2 class members are not yet done, so you have 2 more minutes. Waiting on you. 1 more question to go. All right, so everyone is done, and congratulations to Kaylin Tyler Smith, and the Rihanna is second, and Tyler Smith is third on the leaderboard. So as you can see, I think question number that's a question number 4, number 9, and probably number 18. Let's just review the questions. How many significant figures does the following number have? So four class members got it right. The correct answer is 4. So only so first of all, the first 3 zeros are not significant. Can somebody explain why? Why are these 3 zeros not significant? Can you hear me?
Yes, I can hear you.
Yeah, can somebody tell me why the first 3 zeros are not significant?
Because they're leading zeros.
The leading zero. So any zero that comes before the first non-zero digits, before the 2, so those are not significant. Now, this number has 4 significant figures. That obviously means the 2, 0, 4, and 0 are significant. Could you explain why the 0 is significant?
Because it's in between.
It's between 2 non-zero digits. Correct. That's rule number 2. And then the last 0, why is it significant? Five class members got this right. So could you tell me what was your reasoning, or did you just guess? Of course, you can guess sometimes when you're not sure what to do, but I'd love to hear why.
Because it's a trailing 0.
Okay, and it's a trailing 0, and it's to the right of what? A decimal point. Okay, trailing means it's at the end of the number. And then secondly, is to the right of a decimal point. There's a decimal point in this number. So any 0 that falls to the end of the number will be significant. So if we had 5 zeros behind this other 0, all those zeros will be significant because of this decimal point. The only time when trailing zeros may not be significant is when there is no decimal point at all in the number. When there's a decimal point, all trailing zeros, that's the zeros that come at the end of the number, are significant. Okay, so here only one person got this wrong. So these 4 zeros are significant because the 4 zeros are sandwiched between 2 non-zero digits. And then the last 0 is significant because it's a trailing 0. So it's at the end of the number. It's also after a decimal point. It's at the right of a decimal point. Number of significant figures here is 3 because first of all, here you have a trailing 0, which is significant. So it's a 0 at the end of the number and to the right of the decimal point. And then the other 0 is between 2 significant digits. So basically, any zero that's sandwiched between two significant digits is also significant. And then here we had three class, sorry, yeah, 4 of the 7 class members got this wrong. The number of significant figures in 10 liters. So actually this problem is inaccurately worded, or the answers are not, there's a problem with the answers because here you cannot simply tell by looking at this whether the 0 is significant or not. So the correct answer to this number should really be 1 or 2. So there may be situations where this 0 is significant. There may be instances where it's not significant as well. So the correct answer here should really be 1 significant figure or 2 significant figures, because there's no decimal point. So we don't know for sure if this 0 is significant or not. And then here, so this again is a situation where these 2 zeros could be significant or not. So you could have 1, 2, 3, 4, 5, 6, 7. So you could have 7 or 6 or 5. So the correct answer could be 7 or 6 or 5. But if we're going with the assumption that no decimal place means all the trailing zeros are not significant, then you would go with 5. And that's the convention that many textbooks take. But again, I wanted to be aware that there is ambiguity when no decimal place is present. The answer could be 5, the answer could be 6, and it could be 7. And then here's around using significant figures math rules. So when you multiply 2 numbers or 2 measurements, the answer should only have as many significant figures as the least accurate number. So the least accurate number here, or the number with the fewest number of sig figs, is 11, which has 2 significant figures. So the answer can only have 2 significant figures. And clearly here you can see that 103 multiplied by 11 rounded to 2 significant figures is 1100. And you can see clearly this is a situation where these zeros are not significant, but you also cannot discard them, because if you discard this, your answer will not have the correct magnitude. You cannot say 103 times 11 is 11, or 1130 or 1133. It has to be 2 significant figures. So the zeros here are just placeholders. Now, when you divide 2 measurements, the same rule for multiplication applies. The answer cannot be more accurate than the least accurate measurement. So the first measurement has 1, 2, 3, 4, 5 significant figures. And this one has 4 significant figures. So 5 significant figures divided by 4 significant figures, the answer must have 4 significant figures maximum. And that happens to be this answer. So this is the correct answer. When you multiply, the same rule applies. So 2 significant figures multiplied by 3 significant figures, the answer should have 2 significant figures. And then here, how many significant figures? All the zeros are significant. You have a trailing 0, and then you have 4 zeros sandwiched between 2 non-zero digits. So you have 8 significant figures in this number. And then here, when you subtract numbers, the rule that governs subtraction and addition is decimal places. So the first measurement has 1 decimal place. The second has 2 decimal places. So the answer cannot have more than 1 decimal place because the number that is the least precise defines the precision of the final answer. So the correct answer will be 1.5 because it has 1 decimal place, which is the same as the least precise of the 2 measurements. So again, take note, when you're adding or subtracting, you look strictly at decimal places. When you're dividing or multiplying, you look strictly at significant figures. So how many significant figures here? 3. The first 3 zeros are leading zeros, not significant. The 0 between 2 and 4 is significant because it's sandwiched between 2 non-zero digits. How many significant figures here? So the correct answer is 3, 4, or 5. So 3, 4, or 5, because these 2 zeros could be significant. One may be significant while the other is not, or both may not be significant. So the only way to communicate and remove ambiguity would be to write this in scientific form. If you had 3 significant figures, you write it as 1.25 times 10 to the 4. If you had 4 significant figures, you write it as 1.250 times 10 to the 4. If you had 5 significant figures, you write it as 1.2500 times 10 to the 4. How many significant figures here? This is a repetition. So, and I guess because the questions were shuffled. So the correct answer is 8. Now here is addition. Again, the rule for addition is you look at decimal places. So the first number has 2 decimal places. The second number has 1 decimal place. So the answer is going to have 1 decimal place because it cannot be more precise than the least precise measurement. And if you look at the answers here, only this answer has 1 decimal place, and it's therefore the correct answer. Subtraction. So you have 2 numbers, no decimal place. So if you subtract 14, 21 minus 34, the answer is 1387. No decimal place and no rounding. You don't have to round anything. And then here you multiply 3 numbers. You multiply 3 numbers, 3 significant figures, 3 significant figures, and 5 significant figures. The answer is going to have 3 significant figures because the answer for multiplication cannot be more accurate than the least accurate measurement. Subtraction, you have 3 decimal places, 3 decimal places. The answer is going to have 3 decimal places. So if you know these rules, you can get to the right answer even without doing any calculation, because if you look at this answer choices, only one has the correct number of decimal places. So even without doing the actual subtraction, you could just look and tell the right answer. So for addition and subtraction, you look strictly at the decimal places. And then for multiplication and division, you look at the significant figures. Now, if you had more than one answer with the same number of decimal places, then you will need to actually punch this number into a calculator to see which one has the correct numerical value. But just look at these 4 choices, I would tell this has to be the right answer because that's the only number that satisfies the rules for decimal places. And then number 18, multiplication, 4 significant figures. I take that back, 3 significant figures multiplied by 3 significant figures should give you 3 significant figures, and only this answer has 3 significant figures among these 4 choices. And then here, 100 divided by 2.0. So again, we are in the territory of ambiguity where 100, if you treat this as 1 significant figure, divided by 2 significant figure, then the answer should have 1 significant figure, which is 50. So the 0 is treated as not significant. But if you treated the 2 zeros as significant, then you have 3 significant figure divided by 2 significant figure, and then the answer will still be 50 because you're treating this 0 as significant. But the answer cannot have more than 2 significant figures because this number has 2 significant figures. So 50.0 cannot be correct, 50.00 cannot be correct, 50.000 cannot be correct, but this is 4 significant figures, 3 significant figures, and then 2 significant figures. And finally, when you multiply this, you get two significant figures because 0.89 has 2 significant figures. Any questions or comments about today's lesson?
No, sir.
All right. So that concludes our discussion for significant figures, measurements, accuracy. And don't forget, we have 2 meetings in a week. So the next meeting will be on Friday at the same time, 12 p.m., using the same link. So I'll see you in our Friday session. But keep working on the course. Do not fall behind. If you've missed anything, go in and do everything to get caught up before our next class meeting. Remember to be eligible for your scholarship in the fall. You need to successfully complete this course. And like I said before, the focus here is not just the grades, but it's the actual comprehension. Because if you're struggling with this, like the quiz we just took, all your chemistry, biology, physics, math classes will have calculations that require you to know how to round numbers correctly. So we want you to master this basics so that when you get here, this will not be the things you struggle with. So I really want you to understand this as we proceed. We want you to, score, have a good score, a good average on every quiz, but that's not the focus. The focus is comprehending the material and being able to apply this to your STEM classes when you get here. So have a good and productive rest of your week, and I'll see you on Friday.